Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll continue Chapter 5 and look at some of the examples that have interaction in a two-way experimental design. So the example we've been discussing is the Beatles survival time. And just to refresh what we're looking at, I'm paging up. All right, so we've got this two-factor example where we have four insecticides labeled A, B, C, and D. And for each insecticide, we have three concentrations or doses, low, medium, and high, 1, 2, and 3. For each combination of dose and insecticide, we have 4 beetles that we subject to the insecticide and dose, and we ask how long did they survive. The units are in 10-hour units, so 0.31 indicates 3.1 hours. We saw the marginal means, or the cell means before, so this number 0.413 is the average of 4 beetles at insecticide A, dose the low dose. And we looked at all the models for this. For example, paging up and down, we broke each observation for factor 1, factor 2, and the beetle has a certain mean, and that mean we broke into the structure of the grand mean plus the insecticide effect plus the dose effect plus an interaction if the differences between levels for one factor depend on the level of the other factor. So now page down, and here we are at the Beatles example. So the first thing we're going to do after we've read the data in and we've converted it to long format is we're going to calculate means. And we're going to use the plier package to do this. So first we can calculate the grand mean over all the beetles. That's the average of the column hours 10. The hours 10 column has the survival time of all 48 beetles. And so the grand mean of that is 4.8 hours, roughly. Pliers, where it's useful to use plier here to summarize by group. So if we input the long data set in there and don't specify any factor level, so this is a way of identifying an empty, that we're going to average over everything, we're going to summarize and calculate the mean, put that into a variable m, by calculating the mean of the hours in the Beatles long group. And so we'll assign that to Beatles.mean, and the m variable, which we assigned up here, is that same number, 0.479. All right, so now we can summarize by dose. So for each dose, let's calculate the mean. And so here we have, and we're going to assign that to Beatles.mean.d. So in here we have a dose column now. Notice before the ID column was blank. Now by dose, we have low, medium, and high, and here's the mean over each group. So one thing to remember here in the plier package, what ddply does, ply is short for apply, so it's going to apply a function. The function it's going to apply is it's going to summarize using the mean function. D and D means that the input is going to be a data frame, so that's the Beatles.long, and the output is also going to be a data frame, that's this Beatles.mean. And this argument indicates what group. So okay, the apply function does 3 things. The first thing it does is it splits by a factor variable. And in this case, let's look at dose. It's going to split by dose. Then it's going to apply the function. It's going to apply the mean function and apply that to m. And then it will combine the results of each group into a data frame. And so here's the data frame that it combined. For each dose, we've got the mean. So it splits, applies the function, and then combines the results into a single data frame. Here's the by insecticide. Same code. I'll put it into an object called .i, and for the insecticides, here are the means. So these are the same numbers as we had in the table above in the previous video. Finally, you can do combinations of factor levels for different factors. So for each dose and insecticide combination, calculate the mean. That's over 4 Beetles. These are the cell means that we saw in the table above. And the reason for creating these summaries we'll see in a moment. So let's scroll down, and we're going to take a look at this plot on the left, because I think that's the more useful plot. These two plots give the same information. On the vertical axis is the hours. On the left, we've got encoded on the x-axis the dose, and then encoded as colors are the insecticides. The plot on the right does just the opposite. It does insecticides as the horizontal axis, and colors are dose. But I think looking at the doses, low, medium, and high, for each insecticide, for example, A is red, and see that the low, medium, and high decreases over time, or over the doses, I see that as a more intuitive way of thinking about this problem, rather than looking at insecticide A and seeing low, medium, and high going red, green, blue, and seeing that the insecticides are different for different doses. I like thinking of insecticides and seeing how the differences appear for doses. So I'm going to walk through the code for producing this plot. There's a lot going on. There's, maybe we'll just jump up and down, or I'll just page up and down to look at this. So the first thing is using ggplot for the Beatles.long dataset. Here we're encoding on the x-axis the dose, on the y-axis the number of hours, hours 10. The color and shape is going to be insecticide, and probably that's the, there might also be a group equals insecticide at the end of this line. You can look on the website at the R code to see. And just for the heck of it, let's go down to ggplot. Okay, so it's this code here, and there's no group there, just color and shape. So we see everything on the slide right here. All right, now we need to add some layers. Now that we've defined the axes, let's add some layers. So the first thing I do is I add a horizontal line where y equals 0, and that I make that black. So all that's doing is it draws this one horizontal line at the bottom. Not a big deal, but I find that reference line is really valuable to be able to have a basis for judging where the other numbers are. And I'm setting alpha equal 0.3, so it's sort of a gray line. Next, we're going to add a layer that has the box plots. So these, remember these box plots, see how many box plots there are? Okay, there's 12 box plots. Each box plot summarizes 4 observations. Now this may not be a great way of presenting this data, because a box plot is a 5-number summary. It's the minimum, the first quartile, the median, third quartile, and the maximum. And we're using 5 numbers to summarize 4 observations. So just something to be aware of. You can see, for example, that the median is in the middle of the 2 middle observations. Not a big deal. I find the box plots a bit helpful because you can see the range of the data a little more easily than using your eye to connect the dots. The dots are already connected by the box plot. On top of the box plot, I plot the points. And I'm going to dodge their position a little bit. And that's what makes, oops, sorry about that. That's what makes both the box plot and the points dodge left and right. So for the low, I've got the 4 insecticides and the boxes don't overlap. So that's where the dodge is happening. Also, the points here are a little bit transparent. That's probably because here alpha equals 1/2. Okay, so the opacity is only a half. I'm also going to add a point here of size 4, which has the means. So these are the cell means. .di, just above, I'll page up, did for each dose and insecticide combination averaged the 4 beetle survival times. So these 12 cell means are what's being plotted with this geome point. The y value is the mean, m, inside of this summarized data frame. Size 4 gives me bigger points. So this big green triangle, this big red or big blue square, big red circle, big purple plus sign. I don't love the plus sign because it has less salience than the other 3 filled in shapes, but that's what we have. So that's connecting the means. Then I've got geome line, which is going to connect the dots. So group equals insecticide means that for each insecticide is being treated as a group, and the lines are connecting all the points within each group. And so that gives us these profiles to help us determine whether there's interaction or not. Finally, I'll add some labels, in particular the title. And the only difference between this code up top and the code in the bottom is the swapping between insecticide and dose in terms of what's being encoded on the x-axis or as color and shapes. All right. And a way to do this sort of in a more simple way in the base graphics is just to use the function interaction.plot. You say dose, insecticide, and the y variable, and we've got dose along the horizontal axis, insecticides are the line types, and then the hours is the vertical axis. And so these profiles that you see here are just the plots of the means, the cell means for all the combinations of groups. This is a pretty good place to start if you just want to get a quick plot of the interaction, but I think this is much more valuable. In particular, one of the assumptions of our model is that the variability for the residuals is the same for all combinations. And notice one thing here, the high group is very low variability, but the medium and low groups have much higher variability. So we don't see that in the plot below, in this interaction plot, because this is just the point summaries. So this is one of the reasons I always emphasize plot all the data and then annotate that data with summaries when it's helpful. All right. So finally, let's fit a model. So I'm going to skip all the text because the text describes what I'm about to say. So we're going to use the lm function to fit the response variable hours 10 tilde, and then here is the model for the mean. We have a dose effect, we have an insecticide effect, and we have a dose colon insecticide interaction. Another way to specify all 3 components in just one line is dose multiply insecticide. That multiply in this functional form actually expands into each of the main effects as well as the interaction. All right, so we fit the linear model, and notice I sort of get out of control with labeling these things. You don't need to do something quite as complicated as this. But I'm saying this is a linear model object. The response variable is hours, and then it has a dose insecticide and dose insecticide interaction. So that's what my labeling convention is. Do what suits you. I guess one advantage to doing this is if I decide to drop the interaction, then I rename my object without the .di, and I always know what's in that object. So I put myself through a little additional pain up front so that later I always know what those linear model objects are. All right. In the car package, we'll use the capital ANOVA function and look at the type 3 sums of squares and test the effects of dose, insecticide, and the interaction. Now, let's take a look. So one thing to point out here is that we've got 6 degrees of freedom in the interaction. That makes sense because the degrees of freedom was the number of rows minus 1 times the number of columns minus 1. So we have 4 rows, 3 columns, subtract 1 from each of those, multiply them together. 3 times 2 is 6. All right. This suggests that we don't have strong evidence for interaction. We do see in this plot that all these lines are not parallel, right? But there's also quite a bit of variability. Look at this green spread, right? These 4 points span from about 5 hours up to almost 13 hours. So we have such big variability that's contributing to the residual sums of squares, and that's why we're getting a fairly large p-value here. There definitely seems to be some effect of insecticide, but surprisingly not a big effect for dose. Okay. And these estimates, as I've mentioned before, are hard to interpret because they're all relative to the intercept, which is the baseline reference group. In this case, dose is low, is the intercept. So we have medium and high effects from that, and insecticide A is in the intercept. So this mean here is the average survival time for the low dosage of insecticide A. And you'll recognize this number as the first cell value in the table. And actually, by adding the effects of medium and of the dose effects estimates and the insecticide estimates, as well as the dose and insecticide interactions, all of the values from the table above can be gotten from all of these numbers. Shall we try one? This will be annoying for paging up and down. So let's do, just to make things sort of simple, let's do medium dose for insecticide B. So from the intercept, let me bring up this stupid calculator again. Okay, so we're going to start at the grand mean, 4125, and we need from that baseline group, we're going to go from low to medium in terms of the dose. So to that, we're going to subtract 0.0925, and we're also going to go from insecticide A to insecticide B. So we added the medium, and we're also going to add this part for insecticide B, plus 0.46750, and then the interaction. So we also have this additional amount here, dose medium insecticide B. Well, I'm going to add that number, 0.0275, and press enter. 815, that should be the cell mean for the medium dose for insecticide B. Okay, I'm going to page up. I didn't practice this ahead of time, but I am confident. Okay, so insecticide B, dose medium, 815. All right, got it. And so from those effect estimates, we can recover all 12 cell means It's just that we used a model to parameterize these means. All right, so I'll page way down again, past our pretty plots. Okay, so there is the parameter estimate table. And these tests over here are really not the ones that are very interesting, because they're all just, does insecticide B at the low dose differ from insecticide A at the low dose? Everything is relative to this baseline group. Not really interesting generally. All right, so let me page up again at our model. And what we found is that when we looked at the type 3 sums of squares for the interaction, we saw, at least at a 0.05 level, that the p-value was fairly large. It was 0.11. So we might, at this point, decide to simplify the model. And there's a really important hierarchy here. We have dose and insecticide in the model, and we cannot drop dose, even though it has the largest p-value, if a higher order effect, like this interaction, also includes dose. So we have to keep these main effects in there as long as we have this interaction, which means the first term to go in this case is going to be the interaction. All right, so we can use the update command function to start with this full model with the interaction and update it by subtracting the interaction. Notice I'm going to assign this to this object. It doesn't have the interaction label on there. And if I just look down here for a moment, this does not have the interaction anymore. So it did what we expected it to do. When we look at the type 3 sums of squares, we see, aha, both insecticide and dose are significant, conditional on the other one being in the model. And similarly, these effects are all relative to this baseline group, not that interesting right now. Let me page up again and just emphasize what this means. We've determined that there was not an interaction in the model, which means that we want to think of these lines as actually being not statistically different from being parallel, which basically means what is the average profile here? Basically, sort of that goes down from low, medium to high is the final estimated model. Okay, we don't have a good picture of that. I apologize, I didn't draw one. Okay, let's do the multiple comparisons. So we just have the main effects. So we're going to compare over main effects. So we can use the general linear hypothesis test function, and we want to test the linear functions of dose, controlling for multiple comparisons using Tukey's honest significant difference, as well as for insecticide. And we're going to put that into this object and look at the summary. And oops, something just happened. My screen walked away from me. And we're actually going to do Bonferroni. So this is sort of strange. We could have done the Tukey, left it at a Tukey multiple comparison, but the point is that I specify what the linear functions I want. I can specify any correction for multiple comparisons, and then when I output the summary, I can readjust for another multiple comparison criterion or correction amount. So I'm going to give the Bonferroni corrected comparisons. And notice for dose, I've got 3 lines. I'm comparing medium to low, high to low, and high to medium, and asking whether the difference between those equals 0. What we find here is that comparing medium to low, on average, the estimate is very small, 0.07. The standard error is about the same size, so we have a t-statistic of about 1, p-value of 1 after Bonferroni correction. So there isn't a difference between medium and low. How about high and medium? There is a difference. Yes. And how about between high and low? A much bigger difference. Okay. 0.34. Basically 3.4 hours difference going from high concentration to low concentration. And it's negative because high had a small survival time, low had a large survival time, so this difference of a low number minus a high number is negative. Then we can compare insecticides. On average, how does insecticide B compare with A? Survival time is about 3.6 hours longer using insecticide B, and so on. So there seems to be a difference between B and A, not between C and A, yes between D and A, and so on. And another way to view this, as we saw before, is if we plot this summary of the general linear hypothesis test values, we get these confidence intervals, which show what we saw in the table above. In particular, maybe just looking at dose for now, compared to the high group, high has a much lower survival time than low because we have the mean to the left of the vertical line of 0, and the confidence interval doesn't include 0. And high and medium are also statistically different, but medium and low, the interval contains 0. There's not a statistical difference there. All right. Go ahead and read the interpretation of the dose and insecticide effect. I believe I've adequately discussed these already, but it's worth a few minutes to read that and make sure that all that is very clear. I'm going to come back and do the battery example in the next video.